Hey guys, welcome to day 7 of solving LeetCode daily challenges. So today's problem is power of 2. So there is a given integer number n and we need to return true if it is a power of 2 and otherwise we return false. Let's say we are given with a number n equals to 1. We can express it as 2 power 0, so we return true in this case. What if we have n equals to 15? In this case, we can't express it in the power of 2, so we return false. Let's see how to solve this problem. So given that n can be negative number, 0 or a positive number, can we see a base case in this, like what if n is negative and what if n is 0? Let's say n equals to minus 16. It can be 2 power 4, but it is minus. So can the power of 2 be negative? No, right? So we'll just return false. And when n equals to 0, then we can't express it in any of the 2 power x. So let's just return false in this case also. Can we write like n is less than or equals to 0? Then we just return false. So we have eliminated these both cases. Now let's see what if the n is positive. So let's first check for divisibility condition. Let's say while the particular n is divisible by 2, we just reduce the n by 2. That means we divide it by 2 and then we reduce one power. Here we are reducing the power of the number by 2. Let's take a simple example like n equals to 16. So we can see that it's divisible by 2. So in this case, the n will become 16 by 2, that is 8. We see that it is divisible by 2. We can say now n will be equals to 4, that is 8 by 2. And it is also divisible by 4. So we reduce this particular 4 to n by 2, that is equals to 2. Now we see that 2 is again divisible by 2. So we can reduce it by 2 as 2 by 2 equals to 1. Now we see that 1 by dividable or remainder of 1 by 2 is not equals to 0. So we just stop here the reduction part and move to the next, like let's just compare n equals to 1 or not. We got that n equals to 1, so we can return true in this case. But what if n equals to 5? Let's say n equals to 5 and it's not divisible by 2, right? So we just compare it to 1. It's not equals to 1, so we just return false in this case. Let's think of some another approach or optimizing it, because we are reducing it here exponentially, right? So let's think bit manipulation. Okay, so first we'll see if n is greater than 0 or not. Is n greater than 0? If it's greater than 0, then only we'll move to the next part, that is n should not be negative or 0 to be the power of 2. So let's next see if n and n minus 1 is equals to 0 or not. Why this case? Let's say if n equals to 2 or if n is in the power of 2, then it will have only one bit with 1 as the most significant bit. So let's take 2's binary, that is 0 1 0, and 4 can be represented with 1 double 0, 8 can be represented with 1 triple 0, and 16 can be represented as 1 0 0 0 and 0. We can see that we have only one bit in the number of power of 2's. So let's say why we are taking n minus 1 here. What if we subtract minus 1 from the given number? Let's say 2 minus 1 will be 1. So 1's binary will be 0, 0 and 1. We see that the next 0 is becoming 1. And let's see 4 minus 1, that is 3. 3 will be equals to 0, 1 and 1. We again see that it is the first, it has 1 in the 4, but we see it's all right bits are equals to 1. Let's see this condition also as -1, that is 7. So 7 can be written as 0, 1, 1 and 1. We see that all the bits are equals to 1. What if we do AND operation to both the numbers? Let's say we take 2 and 1. When we do AND operation in this case, so 1 and 0, it will be 0, 0 and 0. So it is equals to 0. Only if the given number is 2 power, then only we can satisfy the given condition, that is n, and n minus 1 will be equals to 0. So let's see if it works or not. Let's say n equals to 5. What if the given 5 is equals to 1, 1 and 0? Oh, sorry, 1, 0 and 1. So now 4 equals to 1, 0, 0. And what if we do AND operation in these two numbers? We get as 0, 0 and 1. So it's not equals to 0. So we return false, as it cannot be expressed in the form of power of 2. Let's again see of another approach. Let's take I equals to 0, and we need to check, like, while 2 power I is less than the given number, we just increment the I value by 1. Okay, so what if the given number exceeds n, or what if the 2 power I exceeds n? We'll just compare if 2 power I is equal to n or not. Let's take an example like n equals to, suppose it's 5 again. Now let's say I equals to 0. It will be 2 power 0, that is 1. It is less than 5, so increment the I value by 1, that is I equals to 1. Now let's say 2 power 1 equals to 2, which is less than 5, so increment the I value by 1, that is 2. Now let's say 2 power 2 equals to 4, which is again less than 5, and now increment the I value by 3. Let's see if the 2 power 3 is less than 5 or not. It is 8, which is greater than 5. So we just stop it here, like the incrementation will not be done further, and I value is 3. Now let's say if 2 power 3, that is 8, is equals to n, which is 5, it's not equal. So we just return false. What if n equals to 2? Let's say I equals to 0 and 2 power 0 equals to 1, that is less than 2, and I equals to 1 and 2 power 1 equals to 2, which is again less than 2, and next time we see that 2 equals to, no, we see that it's not less than 2, it's equals to 2. So we just stop it here, and let's take I equals to 1 and compare if 2 power 1 is equals to the given n or not. We see that it's equal, so return true. Let's do the code part now. First, let's go for first approach, that is checking the divisibility of 2. Let's say first if n is less than or equals to 0, that is negative, and 0 will be eliminated in this case. Return false. And next, while n is divisible by 2, we just reduce n by 2. And if it's false, now we'll just return if n is equals to 1 or not. Let's run this code. Yeah, the code runs fine. So let's submit this and check if it's possible for every possible case or n. Yeah, the code runs fine for every n. Let's move to the bit manipulation part. What we need to check in the bit manipulation part is return n is greater than 0 and n and n minus 1. n on n minus 1 equals to 0. Let's run this and see if it's correct. Yeah, the code runs fine, and let's submit it. The code works well for every possible n value. Let's see another approach, that is checking the power of the number. That is, let's say I equals to 0 first, and while 2 power I is less than n, what we need to check, if it's less than I, we just increment the I value by 1, and if it's greater than n, we just return if the 2 power I is equals to n or not. The code runs fine. Submit it. Yeah, the code runs for every possible case. So let's think of a time complexities now. So let's first see the time complexity of first approach. It will take log n for reduction of n to 1, or let's say if it is divisible by n, we just reduce the n by n by 2. It takes at most time complexity of order of log n for this case, and let's see how much time it takes for this comparison. It just takes 1, that is time complexity of the bit manipulation approach will be order of 1, and for this case it takes the time complexity of order of 1 again. Why? Because we are just incrementing I by 1, and for every case we are checking if it is less than n or not.
So that is it for today. If you have liked the video, please like and subscribe my channel. Thank you for watching.